The example Stockfish 8, I think, is 40,000 lines of code, and mine's better than it. So there's a difference there.
What language?
Python. Python running off of C. So C because it's fast, Python because it has support for machine learning.
You optimized it with C code?
No, I optimized it with a Monte Carlo search tree.
But the interpreter is C.
Yes.
Oh,
Yeah. Yeah. So it compiles in C, so it's faster. But all the heavy front end is on TensorFlow. So it's kind of slow, but it's GPU accelerated. So I got it training. It trained in 70-something hours without any stops. So I didn't like stop it at night. I just slept with it in my room going. Really hot. It's great. I didn't sleep much of that. 2 weeks or a week. Decision trees are about as simple as you can get, just decision graphs. You probably did these many times in high school and middle school. But it's automated. The best part about decision trees is you can understand what's happening. It's very simple. You can just look at it and be like, okay, do you want to play golf? Is it sunny? Yes. Is it above 70% humidity? Don't play it. If it's under and it probably feels good outside, play it. Is it going to rain? Don't play it. And it's as simple as that. The only complicated part about decision trees is how many questions you want to ask it. So how deep the tree you want to get, where it goes. It's long time growth for computation. So it gets really, really slow the more layers you add. You usually don't want to go past like 4 or 5 layers to your trees, because then it can get really slow. There's a much better method to do this, which is called random forest, which is a bunch of little trees all added together around the middle. So they're called weak learners because they're just a random model of tree. And then it's every iteration of that random model of tree. And they all work with the same data, and they all give their answer, and then you compile those, and then based off of whichever one was the most voted for, that's your answer. And this is really good because you can learn features of your data. So like, let's say you're classifying a frog. It works really well. So this works well with minority classes because you can see what about the data causes it to be a frog class. Instead of just going for overall accuracy, it goes for, okay, which aspect on which tree works the best in order to get the right prediction. So this is what I would recommend to everyone who doesn't want to learn deep learning or reinforcement learning. This is the best classical model of machine learning. It can learn, it can predict and classify. If you want to do regression, there's other models like NASA and I don't remember one of the regularization engines to do that. But this for prediction and classification is the best you can get, unless you want to get really complicated. And this can be done in 3 lines of code for any of your data. You just plug in X, Y, and then run it, and it'll give you prediction. It's fast too.
Excuse me, can I take 15 seconds to mic you up? Sorry about this. Predicted technical issues wound up being way bigger than I thought they were. So I'll just stick this.
You hear me? Yep. Okay. All right, any questions on supervised learning? Can be general questions, anything, no stupid questions. Yeah.
What is the best alternative to linear regression?
What was that?
What is the best alternative to linear regression?
Linear regression? Logistic regression is really good if you have nonlinear data.
Continuous numbers.
Yeah. Yeah, so if you have complicated data that can't just be a line of best fit, logistic regression makes a curved line to give you all of your correlations in a compact way. Then there's also Lasso. I don't remember the acronym name, but it's LASSO, and that is considered the best regression model for machine learning. That works really, really well for most cases, depending on how big your data is. If your data is really massive, there isn't really the best, like a good regression model out there. You're just gonna have to try all of them and see which one works the best for your type of data. Any other questions? Yes.
If you are looking at, say, like recommendations that you see them happen out on the internet, like creditfor.com does movie recommendations, like Movieland, like Amazon does recommendations on purchase. Are you sort of able to take a guess at what sort of model you're using behind that? Do you ever get a feel for that?
Yeah, but well, they tell you. So a couple of the companies, so Amazon and Google, I know because they tell you. Facebook, I don't know because they don't tell you. I know their sentiment analysis engine, which is fun. So they read the text that you post, and then based off of if it's a happy text or a sad text, it'll give you different advertisements, which is fun. So if you're in a good mood, it'll try to get you to buy things. If you're in a sad mood, it'll try to cheer you up. And it'll try to get you to continually post on Facebook. Yeah, that is a $4 billion project. So, any other questions? No. Okay. Unsupervised learning, the kind of mysterious one, because it's also not really that human interpretable. These are just going to be the main two that I'm going to talk about. There's other ones that are kind of fringe. These are the ones that work the best. This one is made for determining how many types of data you have in your, so how many classes of data you have. And it's really simple. So you give it some number K of how many classes you want it to try to fit. So this one, you can obviously see it has 3 groups. So you could give it a 2 or a 5, and it'll put 2 random points or 5 random points or 3. And you see here, they're just randomly on the screen, and it'll do it iteratively. It'll just try it a bunch of times to see if it constantly gets the same answer. And then it adds all of the area equally for the same distance away on average. And then it'll try to move the circles to the center of what they classified. And then it does this over and over again. So then it regraphs it, and then it counts it again, and then it moves the centers again, and it keeps on shifting a little bit at a time until it no longer shifts by a certain tolerance. So if it moves by 0.1%, you know that's pretty much in the center of where it needs to be. And then you can graph how much error there is between how much far away all the groups are from the center of the points. And it's a nice little curve. And whenever you see the number go here and kind of plateau, you know that's how many groups there are in your data. So if you were to plot this, you would see 1, it would just go straight in the middle, and it would have really high error, so it'd be way up. And then if you did 2, it would be like right here and right here or so. And it would still have pretty good error, so it'd be down, because it's not as bad as just one group, but it's not as good as what it could be. You get 3, it's perfect, it'll go down. You get 4, it's too much, and it might actually go up a little bit more, but it should just continually go down with the same level of error. So it's really easy to understand, and it's really easy to implement, but you have to do 2 different steps in order to figure out what your data actually is doing. So you can figure out what groups it is. So like, let's say you have a list of your population based off of race, gender, height, weight, education history, and you want to figure out, are they likely to commit crime, or do you have a question?
No.
Oh, you're just flexing. Huh?
So like the movie with the rates on?
Oh, yeah. I mean, you could technically do that. And China does do that. It's kind of terrifying.
Is
And
it legal in the West?
not right now. It is legal in some Asian countries that they do it. And then they even have scarier things. So I'll talk about this a little bit later, but there's object detection in machine learning where it can look at a picture and it can tell what everything is inside of it. And then there's sentiment analysis, which can tell what the mood is of the thing it's analyzing. So China's developed a system where it can look at its citizens' faces, and they can determine if they're having negative thoughts about their dictator. And then you can be jailed for it. That's terrifying, and it works. It works. They can tell what you're thinking because you have micro expressions in the cameras, because there's cameras all over every street. the micro expressions can tell you what a person's thinking, if they're lying or what they're feeling. And it will be like, that person's lying, they're having bad thoughts. Because you'll be like, do you love your leader? And they'll be like, yes. And it'll be like, liar. And they'll, there's a lot of security involved in machine learning, thankfully. It's one of the biggest aspects of machine learning is just cybersecurity. So we're trying to get it to be illegal everywhere and to be a human rights violation. But right now, you can't tell what your citizens are thinking and jail them and execute them for it. So, toss up. Any other questions? Okay, happier thoughts. Dimensionality reduction. It is the process of reducing complexity in your data. So that is a really complex model of a three-dimensional data set. This is the same data set, but in 2D. It does it by searching for correlations in the data. So like, let's say there does a regression model on your data. And then off of similar correlations, it'll get rid of a couple of them. So like, let's say there's a bunch of correlations between race and your eye color and hair color. If there's correlating ones like green eyes and blue eyes both go to a certain level of pigment in your skin, it would get rid of the green eyes one and just keep blue eyes. So it'll take different features that are similar, reduce it, squish it, and then post it. And that will allow your models to train quicker because it has less complexity to train on. So it makes it go much faster. But in doing so, you can actually lose some of the fundamental information in your model, which is bad because then you have a bad prediction. And you don't actually know if it is a bad prediction because you don't know, because you never did the analysis on the complex data because it was too complex. So it's kind of a toss-up if you should use it or not. A lot of people do use it. The most popular one that you guys would want to learn is PCA, Principal Component Analysis. It is the best algorithm for it. It usually has the least amount of error, but it can still lead to packet loss of information. So do it at your own risk, but if you have just abnormally complex data, this would be a good solution to do.
Is that essentially removing some of the outliers?
So you can do outlier detection, which does remove the outliers, but this doesn't necessarily remove outliers. It just removes correlations between data to make it less complex. Any other questions? Okay. Modern machine learning, the fun stuff. I'm going to go over these 5 areas. I'm a reinforcement learning specialist, so I had 5 slides of reinforcement learning, and I got it down to 2. So if I still have a bunch of extra time, I might just talk about reinforcement learning because it's awesome. First one, gradient boosted machines, which is basically just random forest, but more powerful. So random forest was kind of this, where we just randomly grow limbs, and then it would make a bunch of iterations of the same tree. This is a bit different in the way that it goes about it, because it starts with the most simple tree you can have, and then the next cycle, like the next iteration, it does a little bit more complex. Then the next one is a little bit more complex, but it never changes the initial ones. It just continually adds new trees. So it does 2 predictions at the same time. It's predicting what the next tree should be to help it predict the class. So it's predicting the classes all the time, and it's predicting itself. So like, okay, I made this adjustment. It gave me a 3% rise in accuracy of my prediction. I should make this prediction, and then it may give me another 3%. And if it doesn't give a 3% rise, if it actually decreases the accuracy, it'll do another tree that supplements the last one while also trying to improve the score. So it's an intelligent way of building decision trees to get features of your data and to classify it in a very fast way. If you have big data, like let's say you have millions of entries in your databases, this is the one you should use. It is the most complex model. It's the one that requires the most amount of code, but it also gives you the best results. It has over 150 parameters, and each parameter is a different thing you can tune about the algorithm. So this is a very complex algorithm. This is really, really good to learn though. And it does work with small databases too. Like let's say you're in healthcare or finance, you only have a couple of thousand entries. This would still work really well. Or if you have complex data, this still works really, really well. It stops working after you get past like 30 features in your data. So if you just have like a person's name, email, blood type, every medical thing you could think of listed, it would still do pretty well. But the further out you go, the worse it gets because it gets too complex for it to manage just trees. If you had that complex of data, you want to do what the next one is, which is deep learning. Any questions about this? What do you mean then?
Faster and more accurate than, I mean,
All of classical machine learning. So everything I talked about before. So all of like random forest, decision trees.
we're gonna come after then, but before then, before and after. What do you mean then?
Yeah.
Other than A, I'm sorry.
Oh, yeah. I made this in like 2 hours. So spelling errors bound. Any other questions other than spelling? It's okay. Any other questions? No. Just gonna drink my water anyways. Neural networks, the fun one, the one everyone's been hyped about for the last 6 years. It's inspired by the brain, but doesn't really work like the brain. The brain's very complex. We barely know how the brain works. And we like to think we know how the brain works, but we probably don't know how the brain works. This one just is math instead of using electricity in your brain. It has a bunch of inputs, which is this input layer. And this could be anything. It's normally just numbers. It's a tensor of numbers. So like, let's say you have an image that's 256 by 256 pixels. It would be, I don't remember the number. It's like 20,000 different inputs. And then all of that gets connected to a hidden layer. And the hidden layer is just the summation of every point connected to it times a weight. And that weight is what gets adjusted when it learns. And then the next layer is just the outputs of the previous layer. And you can have as many hidden layers as you want, or you can have as wide of hidden layers as you want. And then the output layer is usually some function, like a sigmoid, so you get it between a 0 and 1 if you have a binary classifier. So like, let's say, is this a dog, is it not a dog? 1 is a dog, 0 is not a dog, then it's some probability of it. So if it's 30% not a dog, it's probably it's probably a dog. I said that backwards, whatever. Any questions about this?
Is this related in any way to like perceptrons?
This is a percept, yeah. So
Oh, okay, like Mark Lewinsky did.
yeah, so this was made in the late 60s. It was actually before a lot of the classical supervised learning that I talked about earlier. It was very simple to do mathematically, and I have an example of how simple it is.
A few years back, someone talking about doing something with that, with these massively parallel machines. And lots and lots of CPUs, but I guess the computing power has progressed quite a bit. So
Oh yeah, you can use TPUs now, which is tensor processing units. It does linear algebra instantly, which is really cool. So the training time for CPUs for machine is about 160 to 200 times slower than a GPU. Then a GPU is about, I think it was 2,000 to 5,000 times slower than a TPU. So TPUs, and then the new ones made by Google, the TPU 4.0, is like thousands of times faster than that, but each one costs like $2 million. So yeah, I'm not gonna buy that anytime soon.
wait, we got beyond those old Cray supercomputers.
Oh yeah, no, they're just massive computers with a bunch of heat sinks and like 3 chips. So the heat sinks are like 500 pounds around it, all liquid cooled. And then you have 3 little central hubs that it just computes from. It's pretty cool actually. If you ever get a chance to go to Google, look at if they let you into their labs, go look at their.
Like super cooled with like liquid nitrogen or anything like that? Is it
Not to my knowledge, you can liquid cool. I mean, you can like liquid nitrogen cool it. It's dangerous because then it can get too cold. So to do that, you have to have your machine running at a certain temperature before you add the liquid nitrogen. Otherwise, it'll freeze it and break it. Semiconductors or?
Superconductor.
Yeah, semiconductors, yeah. Yeah.
Super cold. Zero resistance.
Yes. So this is an example of how a deep learning network works. This is all of the possible outcomes from all the different shapes. And this is your input shape. This is what you want it to classify. So when you look at this, all the white lines are positive outputs, meaning that that is correct for what it's seeing. All the black lines means it's the opposite of that. And the gray lines means it's not possible. So what it does first is it gets the two whites and the two blacks. And the reason why these are inversed is because this is a white square and that's a white square. And these are black. So it's saying, okay, that is the opposite it's supposed to be. And then it sends it along the next layer and it tries to group them. And then you see that this group is correct, but it's the opposite because white's on bottom and black's on top versus that. This is wrong and that's wrong just fundamentally. It can't be that. So these get grayed out. So for that, it would be multiplied by 0. So then everything attached to it at the end would all be multiplied by 0. So as soon as you get a 0 in your system, everything attached to it just automatically dies, which makes computing a little bit faster. And then you send these along, and you get this pattern and this pattern as your possibilities. This pattern isn't what we see, so that becomes a 0 as well, which is why these are grayed out. So then you just have this one. Then you have two options. You either have the regular version or you have the inverse version. And right now it's the regular version, so you see a black line going, and then this is your output. It classifies this as 100% probable. Does that make sense? Any questions? Yeah. So that is a correct classification. So this is your input. These are your possible outputs, and it classified it as the input. So it would be correct in this instance. If you were to classify it as, let's say that, it would be wrong, and you would give it a negative reward or a negative. You adjust a cost function. So the difference between what it is actually trying to predict and the real outcome. So like, let's say this is a horizontal black on top. Let's say it predicts a checkerboard. You would say, okay, that's wrong. So what you wanted was horizontal. And it's like, okay, we're gonna subtract 0.7 because it had like a 70% likelihood that it was checkerboard. We're gonna subtract 0.7 from your cost function and we're gonna grow it. It wants to shrink it as much as possible. So if you have a 0% cost function, it means you're 100% correct because you have 0 error. You guessed everything correctly. And its goal in learning is to get that cost function as small to 0 as possible. And it figures out different ways to adjust the weights based off of that using this thing called gradient descent, which is calculus. It's just derivatives. So you follow the gradient downwards until you hit a local minima. And then you know that that is as low of error as you're gonna get. And then if it gets stuck, you have to figure out ways to not get it stuck, which is its own bag of worms. Any questions on that or backpropagation? No? Okay. And here's the fun one. So we're going to talk about two different types of networks that are used a lot today. And that is really useful for business as well, if you deal with any kind of image data or video data. Basically, convolutional neural network is it takes an image or a sound or a video, and it takes some filter of that image, like let's say it's a 3x3 squares, so it's 9 block, and then it runs it through and it gets a little snapshot of what that block is. Then it'll go through the whole image and get a bunch of snapshots, and then it'll take those snapshots and use as an input of a neural network. And then your neural network will classify what those snapshots are. So you can take some image, create new data off of it using these feature maps, and then classify what it should be. And in doing so, it can learn like features of your data. Like let's say that if this is turned on, it knows that something's there. So if it's a 1 and something's there, if it's a 0, nothing's there. So it'll get a bunch of 1s in this area, and then it'll see that its classification should be a 0. So then it'll eventually learn over multiple iterations that, hey, this kind of general shape is a 0. Then it'll learn little parts of it at a time for each part of the network. So like, let's say it'll learn a little bit of a curve, and it'll learn a straight line, it'll learn a little bit of a curve, and it'll learn a straight line. And you have a bunch of numbers that go along with it. Like, so let's say you have a 6. It wouldn't think that the curve would be the same as a 0 and an 8 and a 9. And its goal is to figure out what's the differences between those. So it has some probability between those 3 numbers that it's thinking of. And as it trains, it learns the distinctions between what a 6 and an 8 is, for example, which is really difficult for it to learn. Any questions on that? Okay. The next one that's used a lot is recurrent neural networks. This is basically just a memory mechanism. So all of the machine learning I've talked about so far has no sense of what it's already dealt with mathematically. So it's a blank slate every iteration. All that it has is the updated weights. And then it will make a new prediction, and then it will update the weights again, new prediction, update the weights again, new prediction, update the weights. What this does is a little loop. And this loop keeps information persistent through every iteration. So it'll be like, okay, if the starts a sentence and knows that the subject is probably coming next. So it can learn grammar by having memory of what articles go where and how conjugation works and sentences and subject-verb agreement. It can actually remember that as it's learning by just continually keeping things in its memory. And in classical machine learning, you only have 2 ways to use it. You can either have one-to-one or one-to-many for classification. You're kind of stuck, you're limited in what you can actually do. Now, with recurrent neural networks, because it can guess based off of the past, you can do things like this, where you'll keep information constantly in it and then make output predictions based off of that. And that makes it a lot better, makes it more powerful. This is how sentiment analysis is done. So it'll remember, okay, angry is a bad word, or hate or kill or murder is bad words. Love, happiness, puppies are all good words. So it'll classify what the sentiment is based off of its memory and how all of the words are used together. And it'll develop this really deep understanding of how text should go and, you know, how people are happy or sad, and that's how Facebook does theirs. It's also how Google does a lot of their search history. So they know where you are at all times because of Google Maps and everything else on your phone. And then they know your search history, they know your advertisement history, they know what you eat, they know they know where you shop, they know everything about you. So then they can use stuff like this to create a model of you. So the model will have this recurrent memory, like, okay, they like this restaurant, they like these shoes, they like, you know, whatever. They'll build a model of who you are and send advertisements to you based on the model, which is really, really powerful, but it also requires a lot of resources to do. So most people can't do this, but if you can figure out an intuitive way to use it in your data, this is really powerful to use for, I have a list of uses right there, so we'll talk about that. What should you use? Small companies generally should just learn the simple stuff because it's cheap, easy to do, and you can learn it yourself. You don't need to pay someone to do it. And I would say a good metric is if you have less than 5 features in your data, just go with classical learning. You don't need deep learning. If you have millions of entries, do deep learning just because it's so much. But if you have a small data set, like let's say you're a business-to-business company, you just deal with other businesses, you only have a certain number of features in your relational database, you don't need that complex of an algorithm to use. The bigger companies should start learning all of the classical stuff and then some of the artificial networks, just because typically the classical stuff isn't powerful enough to use at an accurate level. So it could get like 70% accurate, but if you're doing it for business, you want like 90-some+ accuracy. Otherwise, your customers might not be happy. Like they found out that, oh, your algorithm only works at a 75% efficiency. So there's a quarter of a chance that it could just mess up and do something bad, like forget their order or mail it to the wrong place, which would be bad. So deep learning is more accurate, it takes longer, but it's better for more complex data. And if you are in like recommendation engines, shipping automation, text translation, object detection, or stock trading, you really want to do more complex models, no matter how big your data sets are, just because the classical stuff isn't complex enough to solve that hard of a challenge. Any questions? Okay. Uses of deep learning. This is kind of fun list. This is just the things I thought of. So there's dozens of more. Natural language processing, computer vision. Natural language processing is the act of figuring out what text is and grammar and translating from one language to another. Like Google Translate uses NLP now. Siri uses it for speech recognition. Computer vision is the act of taking images and analyzing what is actually in the image. So for classification, object detection, creating video, which is kind of cool. Text generation, caption generation, so they can take a blank photo, it'll analyze what's in the photo, and then it'll give it a caption. So if it sees a picture of a dog, it'll say dog. If it sees a picture of a yellow bird, it'll say yellow bird flying or something. And you can give it more accurate results. So if it wants to be really specific, it'll give it like 5 adjectives, which is kind of fun. Recommendation engines, of course, sentiment analysis, of course. Chatbots, it's how chatbots got so good in the last 5 years. Because before it was really stupid. Like, I don't know if you ever just mess with chatbot rooms. You could talk to them and they would just start repeating things you said. Like if you said the same thing 6 times in a row, it would never say anything else. Nowadays, it learns, okay, this is human emotion, this is human talking as conversation, and it tries to be human. Market research and market analysis, market segmentation. So if you're in advertising or anything else, this is a really powerful tool. It's a lot of statistics, so stuff you're already using, but better. And it would definitely be worth the investment. Predicting, you can predict basically anything. People predict the solar polarization flipping. I don't know if you guys even know that the sun flips its polarity. So it's not north and south all the time. It'll go from north and south to medium, where it doesn't have a pole, to south and north, which is kind of crazy to think about. But it can predict when it's going to happen, when solar flares are going to happen, when earthquakes are going to happen because of those solar flares, when hurricanes are going to happen, tornadoes, where the paths are, how long it'll last, when it'll hail, where it'll storm, where thunder will go, where volcanoes will erupt. It can figure out where gold is on the surface of the earth. There's people who study geospatial data with satellites, and then they mapped all of some part of North America where they know where every mineral deposit is within, I think it was like a 500-mile radius. So they could tell what metals were where, what rock layers were where, and what minerals were where, and what crystals were where, just by satellite images and a couple of geospatial data about the crust of the earth, which is crazy. So gold might actually be all mined up in the next 20 years. So, hey. Yeah, that's gonna be interesting. You can do cancer detection, which has actually been very accurate. Like within, I think the newest numbers were 80-some% accurate for cancer detection, just based off MRIs. And it can be like really small lymph nodes starting to be cancerous. You can tell that it's like that will become a tumor, which is crazy. Outlier detection, which I talked about earlier, it basically is like, okay, this isn't normal. I'll just set that aside. Anomaly detection, which is not the same as outlier detection. It basically is like, okay, this is weird. This isn't an outlier. It's not supposed to happen. Something bad happened in the code. And it works really well for running websites, because then you know, oh, my website just crashed because this anomaly happened, and then you can figure out what the anomaly is. Gold mines, we talked about that. Spam filters has been used for a long time. Flaw detection, time series forecasting, which is one of the biggest. So health and finances are the biggest applications of machine learning, which is one of the things I do. I do reinforcement learning for the application of stock trading. So my agent, it's not, I don't know if any of you guys are familiar with stock trading. There's these new algorithms that trade hundreds of times per second to do like fractions of a penny at a time. But over thousands and millions of trades, that becomes thousands and millions of dollars. So my agents take advantage of that. So they'll know, okay, I can do this and make those stupid agents that just trade a bunch, trade it down, then I can make a huge profit. So there's kind of two battles happening in finance right now between investors. That's the people who are spending trillions of dollars making straighter lines for their internet to trade like microns in a second faster. And there's the other people that trade every 5 seconds that are making more money. So stock might actually just break soon because it's all going to be automated soon. So maybe buy some other options, so gold or bonds. Anyway, threat detection, A/B testing is used a lot. You can automate A/B testing and automatic feedback from your A/B testing. So it'll try hundreds of various versions of your website, and then it'll ask your customers, hey, do you like this? Do you like that change? What do you love about our website? And it'll get feedback automatically. So all A/B testing usually used to take months. Now it can take a week. And you can get real good change in your products. Automation, shadow launching, which is cool. Tesla does this for their self-driving AI. Basically, you take the AI and you take another AI, the older version, and you launch both at the same time. And you don't let your new AI do anything, but you let it make decisions. Then you look at the decisions and you compare it to your old AI. And if you think the new AI did better decisions, you use the new AI. If it had a mistake or if it messed up, you don't use it. So it's a really good way of bug testing your code while also getting valuable feedback with it actually running. Meteorology, I talked about, and there's a bunch more. So I have two and a half models left to go through. I'll hurry through them. Generative networks are really cool because they can generate anything that you train it on. So if you wanted to create images of new things, it can. And I forgot to get pictures of people, but there's pictures of people that these agents create that look like humans. Like 4K resolution images of people that don't exist, but they look like humans. And you can recognize them when you see them again. It is creepy. And you can change your appearance. So you can have, like let's say you have a burn victim. If their face is all messed up, you can take a photo of them, and this will make it so they no longer have burns. They look like they did before they had burns, which is kind of crazy. And you can create new video off of it. So let's say I'm walking past this table, and you don't want the table there. You Photoshop out the table, and the network will actually add legs to my body when I'm walking in the video. It'll be 60 FPS, 4K resolution video. So, and there's a newer version that doesn't even have to do all the complicated stuff of this. So this is going to be the new state-of-the-art for effects in movies, video games. You can make new AI with it, new images, new art. If you want to design characters, you can just say, hey, I want 20 characters of this color variation, do it. And then within seconds, you have 20 unique characters that have never existed before that are uncopyrightable. And it's just like that. So graphic artists aren't going to have to take years on games and movies designing things. It can just be done instantly. So the rate of content generation is going to increase rapidly in the next couple of years. And this is the other all-knowing perfect algorithm that people love to claim. It's basically just evolution. You take a giant pool of random mutations, you set them through the process you want to solve, and then you get a fitness score based off of whatever metric you want to do. So like you're playing Mario, you want Mario to beat the level. The farther it gets on the level, the higher his fitness. So then you measure, okay, these 3 Marios did the best. We're going to take those Marios, we're going to change them just a little bit, but keep them mostly the same and see which ones do it better next time. And then you just rinse and repeat over and over and over again. And the only problem with this is that it gets stuck on generations. So I did this with Mario. Actually, that's why I used that example. It got stuck on the same platform for 6 hours, and it took 12 hours to train. So it can get stuck very easily. And so reinforcement learning is the better option. It just does it better. It's still trial by error, but it's an intuitive way to do it. Any questions on the last 2 things I talked about? Because I didn't take any questions. Nope, okay. Reinforcement learning is basically just animal learning. It's how humans learn. We learn by trial and error. If you make a mistake and someone corrects you, you know not to make this mistake in the future. Or if you make a mistake, you fall down the stairs, you know not to walk the way you did to fall down the stairs. This can be used to solve any game that exists. If you make your problem into a game of any sort, it can solve it. So let's say for classification, you want it to be able to classify things. You just make a game of, say, hey, I have a certain number of points in each area. I want you to decide where the points are going to go. And based off your feedback and what the actual result was, I'll give you rewards for it. So I'll be like, okay, you made a good assumption there, you made a bad assumption there. I'm going to give you 10 points for that, negative 50 for that. And I'll get a sense of what's happening. It's really used in robotics right now, and finance and healthcare a lot, and self-driving cars. You can get them to explore any environment and just learn automatically. So it's no hard coding. Most reinforcement learning agents can just be coded up in 50 lines of code, which you can solve any problem in maybe 100 lines of code if you're intuitive enough with how you set up your problem, this is going to be the future in my opinion, but I'm also biased because I study this. It is really, really intuitive once you get the hang of it, but it's complicated to get into it. I've linked a book on this topic at the very end of it. I've linked a bunch of resources. This is how the general process of reinforcement learning works. You have an agent, whatever it is, so if it's a robot, it's its body. It has an action, so you want it to walk. It takes a step. It is now in a new environment because the environment was at this location, now it's at this location. So you have a new state, and you have a new reward. The reward can be whatever you want. So like, let's say you want the robot to walk from here to that door. Every step it takes this way, it gets a positive reward that incentivizes it to do it again. If it takes the step this way, it's like, no, bad robot. And you give it a negative reward, and it's like, okay, I shouldn't do that again. And it builds this kind of fear mechanism where it doesn't want to make bad choices because it wants to get as many points as possible. So you can use this in really unintuitive ways that works really well. So like, let's say you wanted to finish a maze in the least amount of time possible, you give it a negative reward for every second it's in the maze. So then all it tries to do is just try to get out of it as fast as possible because it wants the best reward it can get, which is always going to be a negative reward, but the negative reward between a -3 and a -2, the 2 is better. So it'll just continually try to get through the maze faster and faster and faster and faster until it gets to the point where it will actually, you can program golf carts to drive by themselves through a track perfectly, and they will actually they will drift through the track in the most optimal angles possible after enough iterations, which is really cool. I saw a couple simulations of that, and it was literally going on the edge of the track with its tires in almost every turn. But it finished it in the world record speed, what you could do. Any questions on that? Okay. So here's some great uses, which I already kind of talked about for some of them. Style transfer, so you can, with GANs, you can take an image and let's say you want it to be green. It'll take every feature of that image and change them all to a different color palette. So or if, let's say you want the screaming guy to look like Mona Lisa, you can take Mona Lisa and it will make the screaming guy into Mona Lisa's face and she'll be screaming, which is kind of cool. You can also make, this thing called Deep Dream, where it just studied a bunch of different images, and then it'll hallucinate on the screen and create new images. And for whatever reason, it was just a bunch of dogs, and they were like sluggish looking things. It was real nightmare fuel. If you're interested after this, look up Deep Dream images, and they're just nightmare fuel. Anyway, face image technology, a lot of the face aging apps, you can take a picture of yourself, it'll make you look younger or older. It's done through generative networks. Verification, video synthesis, so making new video if you want it. So like, let's say you have a mocap, so you have a stick figure with different joints, and you want it to simulate walking with all of its limbs moving. You can take a picture of a person and put it on that mocap, and you can actually make a video of them walking, which is crazy. And it doesn't matter what part of their body you take a picture of, it'll simulate the back of their body too and the sides of their body with very great accuracy. The hair sometimes gets messed up because it's kind of hard to do the spirals, but other than that, it's very accurate. Pose generation, if you take a picture like this, it can make you look like this. It's creepy I don't know how it works. I study GANs, but I don't study that aspect of video generation. It can make new music. So also, not only will it make all graphics and characters and everything like that, it will also make music and voices for those characters and for the movie. So in probably 10 years, you could, one person, make an entire movie that is state-of-the-art graphics, which is going to be awesome. You're going to need a really powerful computer and a lot of spare time, but you could do it. Hacking can be done with it, and so can making fake images for, so like let's say you wanted to hack into a self-driving car, you could change all of the stop signs to green lights, which is kind of terrifying, or red lights into green lights, or any number of things that you don't want it to do. You could turn gas into brake. You could turn off brake. So there's, the cybersecurity on that aspect is really ahead of the hacking aspect right now. So it's still safe to drive self-driving cars, fortunately. But that is going to be an issue in the future whenever hacking becomes so easy because everyone knows how to do it. And then RL, of course, I already talked about this a little bit. Self-flying planes. I saw a helicopter learn how to fly upside down, which is just awesome. It can solve any game. It can be used for manufacturing and inventory management. So like, let's say you want your trucks to come in at a certain time period, but it gets an information that your one truck's running late. So it's like, okay, you 2 trucks go ahead of it when it's normally supposed to go behind it. It unloads both of those, then the new truck comes in. And you have minimal waiting time for your supply chain dynamics, which is really good for business. So if you are in shipping and manufacturing or finance or healthcare, you should get someone to learn RL just because it's going to be the future of your field. You can also use it to control chemistry, medicine, genome sequencing. So recently, there is this competition every year of top-level geneticists that study protein folding. And it's very, very hard to, because you can't create a mathematical model of it. So usually they have like a 10% accuracy or 15% accuracy. And out of 60 genomes, the human team placed with 3 genomes correctly. An AI that was made by people who don't even know anything about DNA placed 30-something. I think it was like 36 out of 60, first try, after it was trained. So our information about how the body works is going to be expanding rapidly. Our information about medicine and chemistry is going to be just exploding in the next couple of years. Yeah. 740, okay. Then these are the learning resources and homework. I have a lot of them. So if you want to learn, these are just the books. This book, if you only want to buy one book, buy this one. You can find free PDFs of it. If you don't want to buy it, you want to steal it, but I'm not endorsing that, so that's actually a link to the O'Reilly videos and articles on how to learn, and then also homework and practicing and learning yourself, and then beginner homework, so learning the language, the frameworks, and how to actually use them on your computer. And then that's my email. So if you have any questions and you want more answers, feel free to email me.